Now it's recording.
Okay, hang on. I want to get my docs out of the way real quick. So I can see what the hell's going on. Why? What happened? Oh, I turned my computer. I see the bottom of it. Is that better?
Yeah.
All right. It's not the cleanest room, but who cares? All right. Sky, it's been good to see you, buddy. I haven't seen you in a minute, but I know
Yeah, I see you.
we talked a lot. It's good to see you. We know we talked a lot in 2020. I bought your book, and because I just think it's fascinating. I'm kind of with you on the consciousness part, but I wanted to ask you some more details about the physics part. But this is an old book, right? I mean, this is 429 pages. This is old stuff. You changed the name. It's
Yeah, the
got new
new
editions.
book it has a new name now. It's called the Complete Guide to Quantum Gravity and has almost 700 pages. And your
Nice.
version doesn't have a lot of important stuff is missing, especially on the gravity side.
Well, good. When you add more consciousness stuff, I'll buy the new version. Hey, but I am intrigued by that novel approach. You want to kind of give everybody an idea of what SPD stands for?
Yeah, SPD is my quantum gravity theory, and the acronym stands for space particle dualism. And so that means that every particle carries its own quantum of space. And that's not so new because every quantum gravity theory quantizes space in some way. But this approach is special in that I don't use the Planck length for the size of my space quanta. I use variable size space quanta. The size is proportional to the energy of the particle.
I've never asked you this before, does it, and I know we didn't pre-discuss this, but does that go below the Planck scale, SPD? Or is it just at the Planck scale?
It's very, very high above the Planck scale. The average size, a non-moving electron would have a size of 10 to the power of 20 minus 21 meters. And
Right.
our Planck scale is 10 to the power of minus 35 meters. So it's
We're not
much
getting the
easier
force.
to test in some particle accelerator. Yeah.
Right. I think we're going to talk about some of the material sciences that we need to kind of make some advancement on. But like your material analyzer that you've talked about, based on that SPD theory, how is this material analyzer going to further your theory?
Yeah, well, normally, well, first of all, you have to know what my theory says about gravity. And it's saying that gravity does not depend on mass or energy, as Newton and Einstein thought, but instead it depends on the number of particles in an object. And so that's really something that Newton could not have thought about because he didn't know that particles exist. He didn't know about the concept of a particle. Maybe a little bit like he sometimes treated photons as small particles, but anyway, he needed something to grow, to increase when the size of objects increase, because he noticed that large planets, they have gravity. And so the easiest thing to go with at that time was mass. And so,
Mass versus weight, correct?
yeah. So the average listener would think that mass and number of particles is the same thing, but it's
Right.
not quite the same thing. I mean, they
Why
would
not?
think that if you have more particles, then you have more mass, but it's not quite that
Right.
simple because
I
Einstein
eat more
showed
hot dogs. I eat more hot dogs. I weigh more.
yeah, right. You have never eaten something with a negative mass, so you can
Oh,
lose weight that way.
celery.
Celery maybe. So Einstein showed that mass is a form of energy, and so as an energy, it has many different contributions. Many different types of energy contribute to mass. So one of them is nuclear binding energy, and that is negative. And different chemical elements have different amounts of this nuclear binding energy. And iron has the most nuclear binding energy. And so that nuclear binding energy is reducing the mass, but not reducing the number of particles. And so
Right.
iron has more particles per kilogram.
Right.
According to my theory, it depends on the number of protons and neutrons, not just any particles, but protons and neutrons, also called baryons. And so that means that according to my theory, iron has the most gravity per kilogram. When you much more gravity per kilogram than, let's say, water or beryllium, any element that's at the beginning of the periodic table. So the G value of iron is the biggest, and then it drops again, but it never drops below beryllium or hydrogen and helium. Well, unfortunately, we can't do gravity experiments with hydrogen and helium because they are not solid, but we can use beryllium. Like this is, for example, a beryllium cube, very shiny one.
I've been watching you drop those things.
Yeah,
your
but
video.
the cubes were not so useful for my free fall experiments. For those, I'm using various spheres. Actually, spheres that are in vending machine balls. So I have two different materials, and then I make sure that the same mass is in both of the spheres, but different material. And so with my free fall adapter for lead and steel, I get time differences of 0.3 milliseconds. And for wood and zinc, or wood and steel, I get 0.4 milliseconds to 0.5 milliseconds, depending on what type of wood it is. If it's dry wood or nutrient-rich wood with a lot of calcium. Yeah.
It's a pretty.
But these cubes are still useful. Initially, I tried to match materials with almost the same density to use in free fall experiments, but this is not so straightforward. The more straightforward thing to do is to use them for my scale balance experiments.
So where you're balancing on each a balance.
So, but let me first tell you about how I show that the gravitational constant is different for every material. I looked at all the recordings, all the measured values of the gravitational constant of the last 200 years. But it turns out that all the values from the 19th century, 18th century, they're not very useful. They're all outliers. And
They all outlie.
outliers.
Yeah.
Yeah, like and so I have a range of acceptable values, which goes from the predicted value of water to the predicted value of iron. And some people have been skeptical because I'm tossing out a lot of values there. But it turns out that if we just accept values from 1971 onwards, then we get the same result. Everything is very neat in the acceptable range. And also those values that were tossed out, they were basically, most of them were just lead values, because in the old days they would always use lead. And
So
modern
is it
values that have to be tossed out are are very unusual, are always relying on some very exotic methods, like using huge water tanks that weigh tons, or huge
right?
lakes,
Right, I was
or
gonna say, or
a
underwater,
huge
right?
container full of mercury, like
Right.
not normal experiment for such large scale experiments. Okay, you would call them intermediate range experiments. it's impossible to achieve sufficient isolation. And if you don't seal off all the air, like I've done Cavendish experiments myself, experiments which aim at measuring the gravitational constant. And in my experience, if you don't isolate all the air, if you don't seal it well, and air comes in, then basically you're getting more fluctuation. The fluctuations are larger, and so you tend to get larger G values.
So it seems like SPD is getting it more specific, more accurate. Now, do you find that, when using your new method, you found some like gravitational constant using different materials then? I mean, has SPD given a more specific
yeah, it
gravitational
out,
constant?
it predicts the gravitational constant, however, extremely precise. For example, Newman measured the gravitational constant of copper and Ponticus, and their measurements agree with SPD to 99.9999
Right.
9%. It's crazy. And also tungsten and so on. And I'm also trying to make sure to not have multiple values by the same person. For example, Luther was measuring the gravitational constant of tungsten, and he got a very, very precise value, 99.9999% accurate in 75. But then he got into the whole business of finding standard values for big G, because he worked together with Kodata to get the internationally accepted value. So he tried to make it fit, the different measurements fit together, and then he moved away basically from his very precise measurement from 75.
Right.
So
clearly,
I only have one measurement by person or by team.
It makes sense. I mean, you've got it narrowed down. Well, I think there's value, right, in gathering info from multiple sources, but consistent.
Yeah, it should be like one person, one vote, like one
person,
one G value.
So clearly, you made a good point.
Materials, it's fine, but one material and you have like 5 different values all by the same person, it skews the data towards that one person.
Right. So you made a good point that we want to measure more accurately. But what about the additional factors? The modifiers, the thing that, okay, so we measure this thing, but surely there's things that affect that, the gravity, the modifiers, and considering these modifiers of mass, like nuclear binding energy, are there other forms of energy that influence the amount of gravity per kilogram?
There's gravitational binding energy, and that has some very strong evidence in astrophysics. So nuclear binding energy plays a role at the level, at the scale around us here. But when you reach the scale of a planet, you have considerable amounts of gravitational binding energy, which is negative. And so Earth, for example, would be 10 to the power of 15 kilogram heavier if you could stretch it out. Right now, Earth has negative mass, 10 to the power of 15 kilogram negative mass. So it's lighter than it would be otherwise. But considering that Earth has 10 to the power of 24 kilogram, I think, it's 10 to the power of 15 is not so much. But when you
balances out.
Yeah, so it's according to my theory, Earth is 0 point something, 0.044, I don't remember quite, percent heavier than we think. But for the sun, I remember it well, it's 0.5% heavier than we think. Basically, the mass of the sun that people believe in now is assuming that the sun is like assuming that the sun is made out of pure iron, because the gravitational constant that you find on Google is basically measured using iron. Stainless steel was measured by Gundlach and by Loire. That's the main difference of the Kodata value.
If we're talking about mass, I mean, mass and energy, I would think that, when we're looking at massive bodies, millions of billions,
so you look at black holes.
Makes huge differences, right?
Yeah, so when you look at neutron stars, they have 15 to 20% nuclear binding energy. Sorry, gravitational binding energy. And black holes have 30% gravitational binding energy. And so that eliminates the mass gap between them, because normally if a star reaches a certain mass, it becomes a neutron star, and if it exceeds that
Right.
mass, it becomes a black hole. And so there should be a needless transition between the masses of neutron stars and black holes. So one has one sun mass, one has 1.1, and so on, and there shouldn't be a gap in between them. And so it turns out that when you account for SPD for the different masses, the SPD masses of them are different. Neutron stars and black holes are both lighter to a certain amount, and that closes the gap perfectly. So it has a perfectly average gap between them.
You don't have to do all the slide rule tricks that they do nowadays. So
They
if you
don't
have the
have
correct,
those. Yeah, I don't know what trick they can employ. This they say
oh,
maybe statistics. There's no solution for
I could show you lots of them. So with the correct mass information at hand, can you determine the exact chemical composition based on that alone?
Yeah, you could so using a free fall experiment to determine what something is made of is very tricky. I mean, here I have two known materials and I test the theory, but you cannot really use it as a material analyzer. And also, who wants to throw down the valuable things? Also, Cavendish experiment, also not very practical. It takes 15 minutes. In my experiment, it took 15 minutes just for one oscillation. People cannot wait that long. And so the new way to do it is to use a combination of a scale and a balance. And so, a scale measures weight, it doesn't measure mass. So at different altitudes, it will show you different results. So for example, if you take a scale that has 3 digits after the decimal point and you use a 100-gram mass, the last digit will change every 60 meters.
Okay.
But people calibrate it so that it shows the right value, because when they use a scale, they don't want to use it for what it's actually built to measure force, to measure weight, not mass, but people use it to measure mass because that's what
Somebody
they're
should make
interested in.
a Excel sheet so you can plug that in and figure it out for you automatically.
Yeah, so I have a balance, which is this thing here. This is
Yeah.
the balance. And so the balance measures real actual mass, which is when you think about ancient balances, they had would put weight both on the left and the right side. And so if
Right.
gravity increases or decreases because of altitude or location, it wouldn't change because it would affect both sides equally. And you would think that maybe in theory where gravity is material dependent, that maybe that's not true, but it's still true because it affects the left side doesn't fall independent from the right side. They form they are one unit, and so it depends on the G value. Basically depends on the material
The
of the
overall
whole
unit.
beam and everything.
Hey,
And that means
I remember
mass.
I remember very well King Midas's story, right, where he gets to the tub and he knows how heavy his crown is. So we only have less than a minute left, and I just want to ask. So you kind of would help to have a Newton scale if people wanted to get a hold of you to help you acquire this new material analyzer. What could they do? How can they get a hold of you? What could they do to help you get there?
Yeah, they can contact me on through my email, skydarmas at outlook.com, or just find me on Facebook. And you can also find my academia account just by Googling